Right. So we're very fortunate to have Anna Maria Ray visiting us from JILA. So Charles unfortunately had to be at a funeral, so otherwise he would have introduced Anna Maria. However, he prepared the following introduction, which I'm delighted to read for you. In 2004, Anna Maria received her PhD in physics from the University of Maryland with Charles. 20 years later, in April 2024, she will be inducted as a member of the National Academy of Sciences. And then Charles also has the following poem that I will read. Our students are found in the world all around. Some come from as far as Colombia. Colombian emeralds sparkle and shine, but none such are ever so fine as our very own Anna Maria. Okay, so that's the poem, and that's Charles' introduction. So now just a few words from me. So actually for her PhD with Charles, Anna Maria received the coveted DAMOP thesis prize. So then after a quick postdoc here, she went to ITAM to do a postdoc. And then since 2008, she has been at JILA. And I've actually never introduced anybody with so many awards. In addition to the membership of the National Academy of Sciences, which I already mentioned, she also received the MacArthur Fellowship, known as the Genius Grant, also the Blavatnik National Award for Young Scientists, and many, many more awards. So Anna Maria has made, she's extremely productive and made many sort of fundamental key contributions to AMO physics, condensed matter physics, and quantum information science. And today she will tell us about Hamiltonian engineering with spin-orbit coupling in an optical lattice clock. I don't know where. Do you know where to put it?
Thank you so much, Alexei. Do you have? I have to put it some here. Okay. Okay.
Sure.
Okay. Well, thank you so much for the very kind introduction. I mean, it's really, really, really nice to be here. All the memories that I had. Last time I was here already was in 2017. I think was for the 10-year anniversary of JQI. So I could not resist, and I'm going to start this talk with 2 minutes discussion because I cannot avoid showing Bill, because actually I came to Maryland, as I said, Alexei mentioned, back in 2000, and I was going to do plasma physics because I got a fellowship to start doing plasma physics with Adil Hassan, and I was very excited about that. But then 2 months after, I saw a talk by Bill, and the introduction of different topics that people were doing in here. And well, after Bill's talk, I could not resist. I said, no, definitely, this is what I want to do. This is what I have to study. I talked to Adil, and so kindly he said, okay, I understand. And he indeed put me in contact with Steve. He was doing cold plasmas at that time. That was my understanding. And Steve very kindly brought me in contact with Charles Clark. And that's how the journey started. So yes, so I think my PhD here was in a very close collaboration between NIST and here. And well, I such a magnificent memories of Charles at NIST. And I was part of the chemical physics department, and my co-plan was kind of my second advisors here. And I hear all very, very, a lot of very nice memories, but of course, a lot of role models and amazing experience meeting fantastic people like Catherine Gevy. So this is something that I can never forget. And of course, not only my original advisor, but I have two different kind of advisors. I mean, Carl William, he was part of the physics division at that time. And of course, I have a formal advisor, Ted Kirkpatrick, here at the university. But of course, was a fantastic journey when I not only learned atomic physics with fantastic theory influence, but also cosmology. So I did part of my thesis work with Bello, who does cosmology. And this is where I learned how nice it is to collaborate with experiment. So I did have so much fun doing my first theory experiment collaborations with people at NIST, Maryland, and amazing summer. So every summer that I was here, it was Kit Burnett and Matt Edwards coming to NIST, and we even ended up singing songs. And so it was a fantastic experience. So I just want to start this talk by saying thank you to Maryland and NIST Gatesburg, because it was the best part of my career. Okay, so now I'm going to present, and I want to start by acknowledging my theory group, fantastic group of people, and including some of them, like Sean Milady, they're here doing a postdoc at the JQI, and of course, amazing collaborations with Junje, that is going to be at the heart of the talk that I'm going to, of the story that I'm going to tell you today, and a great group of postdocs and grad students. Okay, so our main character today are going to be alkaline air atoms. These are atoms that have two outer electrons, and I'm trying to show them here in the second column of the periodic table, but there are others with similar structure as ytterbium here, for example. And why? Because these have a unique atomic structure that they make ideal for clocks. At JILA, strontium is our favorite atoms. Most of the experiments are with strontium. Why strontium or what alkaline atoms? Because these atoms have or exhibit a supercoherence thanks to their unique atomic structure. So they feature a ground state and an excited state that are separated by an optical transition. It's an electron optic transition. But this atom, for example, in the case of strontium, that feature a lifetime that is longer than 100 seconds. And therefore, these systems are ideal for clocks. The way that sometimes it's presented, if you imagine this atom as a pendulum, as a classical pendulum, and you're trying to see what is the quality of this pendulum, and you compute the quality factor, that is the ratio between the ticking rate and the damping rate, is larger than 10 to the 17. So this will correspond to a pendulum that when you start to let it swing, it would have swing for the entire edge of the universe without damping. So this is one of the big advantage of these atoms. But of course, that's not the end of the story. If we want to use these atoms, we have to have an electromagnetic wave, a system that can interrogate this transition that is as coherent as the transition itself, or well, in some degree of coherence. And in fact, one of the big progress that we have had at JILA is thanks to the capability of Jones to build incredible lasers that have a quality factor that now exceeds 10 seconds, and therefore allow us to probe or take advantage of the unique coherence of the strontium atoms. And finally, of course, if we want to avoid any type of systematic effects when we probe this transition, we will need to avoid Doppler shifts. And that's why we are going to trap the atoms in what we call magic traps that don't disturb the energy spacing, because they are identical for the ground and the excited state. And by trapping deeply the atoms, what we avoid Doppler shifts, recoil shifts, and in the magic trapping, star shifts. So this system, the combination of a very nice transition, very long-lived, ideal type of lasers and trapping conditions, allow us to use these atoms for making the most precise clocks that we can do with neutral atoms. So the story is a little bit richer, and besides having these unique single particle properties, that is the orbital degrees of freedom that I mentioned just to make the clock states, the advantage is that there is a lot of tools that we can use to control the atoms. And even though we are having these atoms, of course, they are neutral, but one of the ideas that we have is trying to use lasers in ideas very nicely explored here at JQI, but I'm going to elaborate a little bit more to make these atoms behave as charged particles. And in addition, these atoms has, besides the electronic degrees of freedom, have a nuclear degree of freedom that in the case of strontium can be as large as 9.5. So that means that with these atoms, we have kind of the three pillars, spin, orbital, and charge, that are used or are found in strongly correlated materials to probe unique properties of these systems. Many of them, actually, we don't understand yet. With the additional advantage that instead of having an SU2 system, we can have a system that has up to 10 different nuclear spin states that have some interesting collisional properties that will allow us to actually have new insights into many body physics. Well, of course, this is only for fermionic isotopes that, as I'm going to explain, they're going to be a big player in this talk. So just a big introduction. Maybe all the people are familiar with that, but just to introduce the notation that we are going to have in this talk and explain the problem. So typically, this is not showing so well, but typically what we want to do in order to operate a clock is that we're going to log the frequency of the clock of the laser that we use to interrogate a transition, the G and E transition of the strontium. And therefore, we want the quantity that we care is the laser detunings, that is the energy difference between the laser and the atomic transition. So typically, the protocol follows what is called Ramsey spectroscopy, first developed by a Nobel Prize on Ramsey back into 1989, where we have a block sphere when the atoms start in the ground state. Then we apply this pulse for some time, and we create a superposition between the ground and the excited state by and we apply the pulse for some time t, such that we have a pulse area that defines the amount of atoms in the ground in the excited state. For example, here is going to be by half, and there we have a superposition of atoms in the ground and the excited state that we want. After this, we go to the rotating frame of the laser, and therefore, if we have any detuning in the system, that is, there is this quantity delta is going to act in the rotating frame of the laser as an effective magnetic field that is going to introduce some precession, such that it's going to be the system is going to accumulate some phase because of the energy difference between the ground and excited state. So this phase manifests as a function of the dark time, and then after that we try to detect the accumulated phase by another pi-half pulse that transfer the phase accumulated into population. And that's how we measure what we call the Ramsey fringe, that we measure the population as a function of time. We have this particular Ramsey fringe profile that allows to log my clock laser to the atomic transition because we can have a very well-defined phase, and we have a contrast that is extend hopefully as long as we can. As long as my system is coherent. So as you can see here, of course, the signal that we get depends on the number of atoms in my system. And one of the key advantages of having an array of neutral atoms is that it allows to interrogate many atoms at the same time. This is in contrast with what happens in ion clocks, where typically the interrogation is done with a single ion. So this is where the story starts, that June had the dilemma when he was building the clock, that he wants to use large arrays of neutral atoms in order to have a very large signal to noise, because the more atoms that he had in the clocks, the better its sensitivity. But the problem is that this comes with a challenge that my atoms are not transparent. So the atoms in the clock are going to start to collide, and when they're going to collide, unfortunately, they are going to change the frequency that he was trying to measure it from the clock. So this very intrinsic natural frequency that is our target was going to be modified by the presence of other atoms in the array. That is what is called density shift. So what June had in mind at the beginning when he started to build the clock is that, okay, maybe the way that I'm going to solve that issue, that problem, collisional problem, is because I want to use fermions. And this is where Debbie Jean comes into play very prominently, because she was the person who taught us how we can cool down fermions. And well, we had her expertise at JILA. So June was trying to use fermions as part of the story. So at the beginning, he didn't need an ultra quantum degenerate gas, but the story is going to evolve towards that. Okay. So yes, so as I said, the problem, nevertheless, is that after June used fermions in his clock, still back in 2008, when I was coming to JILA, even with fermions, the clock was seeing an error in the clock coming from collisions that was the second largest systematic in the error bucket. So definitely an important need at that time was the requirement to understand interactions in the clock if we really wanted to take advantage of interrogating large number of atoms. So then, well, a very quick reminder of collisions in the ultracold regime. So we know that when we are going to analyze scattering problems in quantum mechanics, we are going to take advantage that there is a quantization of the angular momentum, and we are trying to expand or understand the collisional properties in terms of partial waves. The key aspect of the collision is that it happens and then atoms go far away, and because of conservation of energy and momentum, the only formation of the collision, it comes in the phase, in a phase that is in the atoms or phase shift. And when we are dealing with ultra-cold temperatures, then the phase shift can have some universal properties and can be characterized by some simple parameters that contain all the information of the collisional properties of the problem. So in fact, so if we expand the phase shift in terms of these partial waves, we find that for L equal to 0, that is the collisions that are the lowest energy collisions that are happening in the system, then are going to be characterized by an scattering length A. And if we go one step beyond, if we go to the L equal to 1, then you can see from this that there is the collisions are characterized by an scattering volume B. So these are kind of single parameters that if I know, I can understand the collisions. The important part to realize, however, is that if I have L equal to 0 collisions, there is no centrifugal barrier, and therefore they can happen even in very cold samples without any energy cost. But on the other hand, if I'm going to L equal to 1, then there is the energy penalty that comes from the centrifugal barrier that I have to overcome in order for the collision to happen. In the case of strontium, for example, this barrier can be very high, 30 microkelvin, and the gas at that time was 1 microkelvin. So that's why June specifically wanted to have fermions in his system. In this case, we were having 3 different collisional channels for the P wave between the ground state, the excited state, and the ground unexcited state. But the important part is that in order to look at, understand what the collisional properties, then at cold temperature, quantum statistics matter. And therefore, if we have identical fermions, this L equal to 0 is suppressed. And therefore, the only collisions that we can have in the system is the L equal to 1. So by working with fermions, we have, in principle, collisions that are mostly L equal to 1, but they are suppressed by the centrifugal barrier. And this is one of the parts that we were going to take advantage of in order to understand the collisions in the clock. So the simple idea that we developed trying to understand these collisions is just to look at what happens of the atoms when they were trapped in a single pancake. So June typically trapped the atoms using a 1D optical lattice, such that the atoms are very highly confined along the direction at which the atoms the clock interrogate the atoms, and most of the motion comes perpendicular to the clock laser. So along this direction, what happens is that the atoms are trapped kind of in an harmonic oscillator from the Gaussian character of the beams. And at these temperatures that are of the order of microkelvin, there are many of these harmonic oscillator modes that are populated. But the important part, as I mentioned, is that we are talking about interaction energies that are very weak. They are P wave dominated because of this centrifugal barrier. And therefore, if we look at the characteristic energy spacing of the trapping potentials that holds the atoms, this trapping potential is going to be of the order of frequency of the order of 500 hertz, around hertz. And the collisions that we are talking about were just a few hertz. So in this picture, the important part is that we can use kind of a perturbative model where we can imagine that atoms are going to remain populate these harmonic oscillator states, but any collisions that introduces change in the harmonic oscillator number is going to be penalized because costs a lot of energy. So the only possible collisions that happen in the system that are dominant are the ones where the atoms just flip the internal levels. So with this kind of an spin model. So the interesting part is that because of the weakness of the P-wave interactions, atoms are going to be frozen in these harmonic oscillator levels, and we can think as them as trapped in this energy lattice. So basically what we have is an spin model where we are going to completely forget motion because atoms are pinned in these single particle harmonic oscillator levels. And the only important that happens is that the spin degrees of freedom that we have to take into account. So in this case, the simpler sphere model opens a road and a path for understanding the complicated collisions that happen in each of the pancakes in terms of a more simpler model. And in fact, this is a work that we did back in 2013 with Alexei, when we were trying to understand how we were going to model these collisions in the clock. So as I said, we are going to have our atoms spin in these single particle harmonic oscillator levels. And what happens is that the atoms are going to see each other just in terms of an effective spin degree of freedom. The important part that to notice is that the atoms are colliding via contact interactions, so they have to bump into each other. But the interesting part is that because they are in this energy lattice, the wave function of the atoms are highly delocalized, like position and momentum are conjugate variables. So in this energy lattice, atoms can interact in these different harmonic oscillator levels with very long range interactions. So that's a big win because actually, in fact, to a good approximation, we don't have to focus in an individual spin, but we can consider, just imagine that our to good approximation, look at the collective spin, that in fact, this is what is being measured by the clock. So if we call SC the total inversion of the system, this inversion is going to be controlled in a Ramsey spectroscopy by the first, by the pulse of the laser that is set by theta. So this is our going to be the control parameter at the beginning of the Ramsey frequency. And in fact, when we look at the collisions, the P-wave interactions, and we try to write an spin model in this frozen energy lattice, what we find is that the Hamiltonian has, besides the single particle detuning, that this is the quantity that Jung wanted to measure in the clock, it has two terms that actually modify this ticking. And these two terms comes into the form of a collective SC square terms and a term that is proportional to the density. And these terms are depending of the P-wave parameters that at that time we didn't know the value. So these parameters are very hard to compute just directly, and therefore we didn't know that. The important part is that in this very simple picture, at the mean field level, this term, what it does is that it creates an effective magnetic field from the other atoms in the array. So this effective term at the mean field levels acts as a change of the detuning, but in the change of the detuning is determined by the inversion of total inversion of the array. And then there is another term here that is proportional to the number of atoms. So with this very simple model, we can see that, in fact, the ticking, a change of the ticking that Jung was measured because of the presence of the collisions were just proportional to the inversion of the cloud and some constant factor that depends on the scattering parameters. So, in fact, that's what Jung measured. So these are experiments done a few years ago when you look at the ticking of the clock as a function of the excitation fraction. And in fact, you see the very nice linear dependence that we expected from this very simple model. And by looking at this, we were able to actually control the experiment such that we operate at a point where there were not ticking, a modification of the frequency of the atoms because of collisions. And that was a very important development and opportunity to cancel and suppress the density shift. Of course, at that time, still the trap was very deep and the interrogation time was mainly limited due to inelastic collisions in the array. So this is perhaps one of the points that we needed to improve. And similar type of suppression of the density shift was observed in other experiments using interunion atoms at least. So, but back in 2014, after we understood better the collisions in the clock with other improvements at the single particle level, actually June's clock was able to reach a sensitivity that is 1,000 times better than the cesium standard. So that was a very important win. And he reached an accuracy of 2 times 10 to the minus 18. And just to put this number in a context, June wants to say that maybe the way to understand it is a clock that never gain or lose 1 second in 15 million years. That is roughly the age of the universe. So that was very nice. So the part that I'm going to tell you now is that in last year, in 2022, we were able to improve the sensitivity by 3 orders of magnitude, open a path to now explore even richer physics. And this was trying to gain further understanding of the collision properties of the atoms in the array. So, and one very key aspect on understanding,
I have a question about the previous slide.
yes, let me go here.
So the 1,000 times better at the top, and there was also the 1,000 times at the bottom that were realized at 2 different times. Were both of these improvements in the same property?
In the same property, yes.
And is that the fractional uncertainty?
Yes, exactly. I think here the 2018 is going to be quoted on uncertainty and precision. This is going to be mostly on the sensitivity. We're going to reach 10 to the minus 21 sensitivity. But June had a paper last week where the precision also was the accuracy, was improved by 1 order of magnitude respect to this. So this is sensitivity mostly. And I'm going to explain what that means. Okay, so what I was mentioning is that one key ingredient that we needed to understand in order to improve collisions in the clock was a spin-orbit coupling, that we know that is a fundamental phenomena in physics. It happens at atoms. It happens also in solid state systems. That is just the coupling between the electron motion and its spin. And of course, it's a relativistic effect. It's in condensed matter physics. It's a very important aspect because it's at the heart of spintronic devices. It's at the heart of the origin of many topological insulators. And in fact, although this is still a holy grail, in principle, if we have systems that have a spin orbit coupling and they're placed nearby a superconductor, then in principle, it's the prediction that we can have that in fact, in theory happens, that you have the possibility to have Majorana modes, and with this a route for topological quantum computation. Of course, this is still a route to look for. But the interesting part is that in the case of the clock, in order to see a spin orbit coupling, the only thing that we need to do is to decrease the lattice depth and let the atoms tunnel across the array. That was something that June was not interested in doing before. So the important part is that we have a clock laser that is interrogating an optical transition. And because the transition is optical, we can see that the wavelength of the laser that is used to interrogate the atoms is comparable to the lattice spacing at which the atoms are trapped. Actually, in the case of strontium, this product is of the order of pi, so it's significant. That means the phase that an atom sees in one pancake is going to be significantly different than the phase that another atom sees in the pancake next to it. So that means that when all the atoms start being identical or down, then the clock drives a transition. And then because of the different phase, the atoms are going to rotate at different directions, depending on the pancake they are. And this is not a problem if the atoms were completely isolated, but as soon as the atoms are allowed to tunnel from one lattice side to the other, then they're going to experience this differential phase. And that's why we call it the spin orbit coupling, because it's a coupling between the position, the spin of the atoms, and the motional degrees of freedom of the position degrees of freedom. So in order to explore it, the only need was to decrease the lattice depth and allow the atoms to tunnel. Of course, this is only one of the manifestation of spin orbit coupling in an optical transition, but there have been beautiful experiments trying to observe and generate the spin orbit coupling in ultracold atoms. And I think here at JQI has been one of the leaders on trying to push and understand spin orbit coupling in atoms. The difference here is that we were trying to use it directly in an optical transition. That is what was natural in the clock. So another way that maybe is useful to visualize the spin orbit coupling is just to go here. The picture that I had before was a picture in position space, but maybe you can try to see this picture in momentum space. By now, I am imagine that the atoms are tunneling along the lattice, and therefore, if we look at the dispersion relation between the atoms in the ground and in excited state, this is going to have the characteristic cosinusoidal dispersion relation with in the lowest band with an amplitude that is saved by the tunneling rate and the curvature of this dispersion, and is going to be identical for the ground and excited state because they have a magic lattice up to just at the tuning that is set by the laser that is interrogating the atoms in the rotating frame. So the idea is that if I have an atom in the ground state, and I'm going to absorb a photon and go to the excited state, because this is an optical transition, I'm going to experience a momentum kick. It's just associated with a Doppler shift that move me from the ground to excited. So flip my spin, but at the same time, modify my motion. And this go, therefore, if I'm an atom in momentum Q naught, is going in the ground state is going to be coupled by atom with momentum Q naught plus the momentum of the laser photon. So a way to model theoretically this problem is to relabel. I mean, I can always relabel the momentum states of the atom. So I mean, still I'm coupling the atom with this energy, but I just relabel or do a gauge transformation. And therefore, in that picture, I'm coupling the dispersion relationship between the atoms in this new basis. This is direct coupling. I coupling the atom in Q with Q plus 5. And this is the laser phase, but directly by the laser. So basically, I can see my system as a bunch of spin 1/2 atoms coupled by the laser that has, and therefore the coupling it's act as an effective magnetic field. In this case, well, the laser coupling is along the x direction, but now because I reshuffle the label of the momentum, I'm going to couple with an energy dispersion that depends on Q. So this is the spin orbit coupling, where Q is going to be just the difference between the energy of the excited state shifted and the ground state. So with that, therefore, I'm going to see that the eigenstates of my system in this of this problem is just going to be eigenstates that are along the x-z direction. But interestingly, the orientation of the ground state that is along the magnetic field is going to depend on the momentum of the atoms, because it's going to depend on the difference between the ground and the excited state. And in fact, so what we were, well, this is one way to see this picture. The other way to see this picture, again, is trying to see that when I go from one lattice side to the other, sorry, I'm here. So if I an atom in the ground state, and I'm going to, it's not working. I think the laser disappeared. Okay, well. Okay, appear again. Okay, we can. Okay, so if I have an atom here in the ground state, I'm going to the excited state absorb a photon, then with some phase phi. Then I tunnel to the other side without phase. Then tunnel emit a photon, but now with different phase because I am a different side, and come back. Then there is a next phase that I accumulate as going around the placket, And this phase is similar to a von Karnoff phase that we accumulate, that a system accumulates in the presence of a magnetic field. So I'm just trying to do the connection between spin orbit coupling and momentum, and spin orbit coupling is visualized in space and also seen as an effective magnetic field. The important part is that, we were able to measure this spin orbit coupling, taking advantage of the very, very narrow character of the laser. So basically, in the experiment, they put all the atoms in the ground state, and then they apply a very narrow laser pulse that only transfer the atoms to the region where they're resonance, and they are not transferred if they're not resonance. Then the experiment blow away the rest of the atoms. That therefore, by doing this protocol, I'm going to be able to select atoms in a specific momentum window that is resonance, and this momentum window could be shifted by actually changing the tuning of the laser. Yes, if I can through the movie here. Okay, it's not working, but okay. Well, you can change the tuning, and therefore you can change the different windows at which you can select you can select the different windows of momentum that we wanted to select. And then after the momentum, for a given momentum window, then you let the atoms evolve in a stronger radio frequency, and then the atoms are going to start precessing at a rate that depends actually on the momentum that they were selected, because remember that the orientation of the spin depends on the momentum window of the momentum of the state. So this is something that we were seeing in the experiments. We saw, therefore, the different radio oscillations that depends on the window of the momentum that we choose. The solid lines are theory, the symbols are experiment. So this is just an evidence that, in fact, the spin orbit coupling, the way that we were seeing, were important and natural component of the clock. But now this experiment was done by reducing significantly the number of atoms in the clock on purpose, trying to see the single particle nature of the spin orbit coupling. But to reality, the clock wants to operate with a lot of atoms. That's the goal. We wanted to increase the number of atoms in the clock. And therefore, you can see that this is going to be detrimental, because the phase of the laser between different lattice sites makes the particles distinguishable. So that means that as long as the atoms tunnel, then what we wanted to be only p-wave collisions, because the atoms are indistinguishable within each pancake. As soon as the atom tunnel, they open a path for actually S-wave interactions. And these S-wave interactions were really bad for clocks. And this is, in fact, what we saw as soon as we let the atoms in a dense sample with exploring the spin orbit coupling. But that was not the end of the story. So then we can bring gravity to rescue, and the new clock now operates along the Z direction. So what is the win of gravity? Well, we know that when gravity imposes an energy penalty of one atom to move one lattice side to the next. So if I'm an atom here and I want to hop to the other side, there is a penalty that is mGA in the lattice spacing that I move from one side to the other. And therefore, if I have a system, then even the single particle eigenstate wants to localize, because this energy penalty can be very large compared to the tunneling rate. And in fact, I mean, very well known, when you look at the eigenstates of an atom in a lattice that is tilted, the eigenstates are the so-called Warner-Stark states that are a function that has, it's a sum of weighting Warner states or localized function that extend over a region that depends on the rate between the tunneling and the energy cost of moving from one lattice side to the other. The beauty is that even at 4 recoil, 3 recoils that are extremely weak lattices, we can still see localization of the wave function. So of course, at 12 lattice is almost totally localized, but as we go to lower recoils, then still we can keep the localization of the wave function. The localization of the wave function. So for us, this was a really win-win. Why? Well, one of the biggest problems that we had is that in order to avoid motion along the z direction, and Doppler shifts and everything, we have to use a very deep lattice. And even though the lifetime of the atoms can be more than 100 seconds, because of light scattering, it was significantly reduced. So if we were able to decrease the lattice depth, even keeping the wave function localized, then the coherence time immensely increased. Moreover, I remember that I mentioned that we still have the experimental P wave inelastic losses. They were extremely suppressed as we go to shallower lattice. So we gain in coherence time. Now, and this is one of the key parts, we have a spin orbit coupling. And by playing with the localization of the wave function, I'm going to explain briefly, we were able to compensate S wave and P wave and again operate at a point where collisions were irrelevant. And this, we call it the magic depth. And then, because of that, we were able to explore new physics and open a path for very exciting new direction. So let me tell you a little bit of the Hamiltonian engineering. So now we have atoms in a Warner star states that we use in a lattice where mostly the overlap is between the nearest neighbor sites. So now if we write the effective spin model that we derived before, besides the interactions between atoms in the same pancake, that is what I showed you before in the prior slide, then now we have a new ingredient because atoms can still be slightly delocalized and have nearest neighbor interactions with the atoms. Thanks to the spin orbit coupling, these are S wave, but because of 5 is not 0, then we have non-zero S wave interactions. The S wave interactions are much larger than the P wave, but they are weighted by eta, between eta, the overlap. This overlap is small because of the gravitational penalty, and this therefore can be compensated of the same order respect to the on-site P wave, where the overlap is very large because it's on-site, but the interactions are P waves. So when we rewrite our model and try to see what was the modification of the ticking rate of the atoms, we see that a new term appeared that is from the S-wave interactions, and now we were able to operate the clock at the point where all these parameters actually vanish. So that's what we told June. We have to operate at a specific lattice depth where this term actually cancels out. And in fact, this is the experiment that they did. This is the change in ticking rate now as a function of lattice depth. These are the experimental points. This is the solid line, is the theory. And in fact, there at magic lattice depth of 12, there was a cancellation of the density shift. At this point, they were able to measure a density shift consistent with 10 to the minus 21. It is basically not relevant for clock operation. And they were able to reach coherence times that was of the order of 37 seconds. So it was a very very important opportunities for the clock. And at this parameter regime, it opened a path for measuring for the first time of gravitational redshift in a very small cloud. So if you remember your general relativity, Einstein taught us that clocks ticking at a different rate, at different altitude tick at a different rate. And in the case of this differential rate is set by the gravitational potential or the local gravity, h, the distance between the two clocks, and is divided by c squared. So this number for the case of Earth is as small as 10 to the minus 19 in a sample of 1 millimeter spacing. And well, there were beautiful experiments back in 2010 in ions where they were able to measure this redshift in a 13 centimeter distance. But now, because the cloud had all this long coherence time and it was not subject to systematic effects from collisions, they were able to record the ticking of two parts of the clock within a 1 millimeter separation. And they did the experiment for 10 days. And this is the recorded and the shift, and they were seeing a shift that in fact was consistent with the one of acceleration of the redshift at a 1 millimeter sample that they had. And this was very exciting, and they were able to see this, and June got this as a coverage measure. So very exciting times. This is one of the physics that allows to explore gravity, and now we are trying to look at the interplay of gravity and interactions. But now let me go a little bit beyond, I'm going to tell you a little bit of the recent generation of clocks that
Just wondering, how big is this device physically?
Uh,
Measures gravity.
well, I mean, it's I don't know exactly. I mean, the cloud is extended over more than 1 millimeter. They have a cavity here that allows to have the size of the cloud is extended more than a millimeter. But I mean, the relative separation is 1 millimeter apart.
Yeah, but I'm just wondering, so for instance, there are these gravimeters by Kasevich and
Yes.
others. So, and I think the main big, well, they're kind of big physically because you have to actually interfere things. So this is a competitor in terms of technology.
Well, I think they're doing interferometries.
Yeah,
Interferometers, I mean, in principle, I mean, I think the phase that accumulate there is proportional to t squared. Yes, it's because it's free fall, and the phase that accumulating during the Mach center interferometer is t squared.
But can you actually measure gravity with this?
That's what our plans with June. Not yet. I mean, this is gravitational redshift, so it has to be coupled from the internal levels. Is a SC, it's a magnetic field gradient. So if you want to measure gravity, you have to do it. I mean, one way to do it is trying to use coupling. I mean, doing a sideband transition between the ground and the state, excited state that is separated by, in principle, many lattice sites. And this is one of the proposals that we have. Yes, I don't know. I mean, this is the phase that we are going to accumulate is linear with time. In Mark Kasevich, he accumulates a phase that is t squared. So there is a lot of things that he gained, and he has a 10 millimeter sample. But this is small, and therefore, in principle, this could be a possibility to do that. Yes. So June call it a space-time sensor. Yes, Alexei? Yeah. What we are trying to look here now is the interplay between interactions. Many body, you can see this gravitational redshift is single particle, but we have interactions. And we think that there is a path in order to use gravity to generate entanglement, or use I can explain you in detail, but there is a path trying to use either start with an entangled state and use see how it decoheres in the presence of gravity, or use gravity to generate some entangle. So there is some paths that we are looking into that. Okay, so how much time I have?
12 minutes.
Okay, perfect. Okay, and I just wanted to go to the next stage. So all the prior ensembles were not operated with quantum degenerate gases. All the prior ensembles were operated with thermal arrays. But the new clocks that you have operates with 3D quantum degenerate gases in a 3D lattice. So he has a three-dimensional crystal with one atom per side, where all the degrees of freedom are really at the quantum level. So he has a quantum degenerate gas of 10 to the 5 atoms, T over TF of the order of 0.1, back in 2019, where he was able to measure a coherence time inside the lattice of the order of 12 seconds. That was significant coherence time in a 3D lattice. Now, last year, you were able to report a system that has a filling fraction approaching unity very close to the trap center. And this was very exciting because it opens a path for the actual exploration of quantum behaviors. So we are familiar with the Hobart model, that is the holy grail model in condensed matter, that is characterized by fermions hopping in a lattice with a nearest neighbor hopping or tunneling J. We have the on-site interactions between one spin up and down atoms in the same lattice site U. Notice that whenever you add a lattice and you restrict yourself to, in all directions, be in the lowest band, we suppress E losses immediately because we cannot have two E atoms in the same lattice site. So it quenches P wave losses immediately. But in addition, we have our spin orbit coupling element that allows us to allow richness on the Hobart model that we can realize. And the important part is that before we were constrained to have the clock laser propagating along the pi directions. But because now we have a 3D lattice, we can put the laser everywhere without blowing away the atoms, and in fact opens up enough for exploring spin orbit coupling. So for example, if we make the tunneling happen mostly in the XY plane and make the Z directions deep, then what matters is the projection of the wavelength of the laser on the SY plane. So for example, if this, if we have, the laser completely perpendicular, then there is no spin orbit coupling because but it's the projection of the XY plane. But if we choose an angle that is 59, we are going to have a spin orbit coupling that can be phi as large as pi. So the angle becomes very controllable. Now, let's try to see what the physics that rules the behavior of atoms in a very deep lattice, what that is unit field. In principle, the naive setting when we have no spin orbit coupling is that if you have atoms in a spin up and down, the atom can tunnel to the other side, experience the energy cost of having another atom, and come back, and they can, for example, flip-flop the spin, or this introduces the spin-spin interactions because the interactions are SU2 symmetric. Therefore, the Hamiltonian that we have is an nearest neighbor, what is called Heisenberg model, with some amplitude that proportional to J squared over U. Well, a spin orbit coupling, interestingly, completely modifies the behavior that we expect. Notice because the orientation of the atoms depends on the position, because it depends on the phase of the laser. So in fact, when we write the effective model in the presence of a spiral generated by the laser, we're going to have a model that is not on the form Heisenberg, but we are going to have a term that has the form XZ, or that is different components in the XXYY compared to the CC, plus an additional terms that are called antisymmetric exchange interactions of the M terms that are typically used in spintronic in solid state systems. So for convenience, we want to rewrite this Hamiltonian as a sigma dot sigma plus some extra stuff that introduces dynamics. I write it that way because sigma dot sigma is completely insensitive to Ramsey spectroscopy because it's a constant of motion for the atoms that are interrogated in the clock. But this term can introduce important difference in the dynamics. And interestingly, that's what we have seen in the experiment. So we have generated, you can now use a three-dimensional optical lattice, have been able to observe the effect of super exchange interactions. So basically we have the 3D lattice, and June is able to actually compare the contrast into different regions, P1 and P2. As we do, we interrogate the atoms with the laser that generate a spiral pattern, as I show, generate a spin orbit coupling. This is very similar to other beautiful experiments done that have seen super exchange interaction in fermionic particles in Emmanuel and Wolfram. In order to avoid having single particle dephasing, June implemented some type of some dynamical decoupling sequence during the Ramsey spectroscopy. So he prepares, introduces a pi-half pulse, let the atoms evolve, and what he does is do comparisons between two parts of the cloud, P1 and P2. So this is excitation function between the two. This form an ellipse in principle. It's a line if the phases are identical, but the important part is that the length of the ellipse is a measurement of the contrast. So he can track the contrast and how it evolves as a function of time during the dark time of the array. And these are experimental points, and just to visualize how the contrast is measuring this experiment. So this plot is a little bit dense, but what he's doing is changing now the lattice geometry and along all directions. So if the prior experiment that I was mentioning was no transverse confinement. So if you allow V perp equal to 0, that's what I was showing before. And this is increasing the BC confinement from weak to stronger. At this point, he sees a constant, this part, we have a coherence time that is reaching about 20 seconds. This is the part where the P and S wave interaction balance. And then at deeper lattice, we have losses and we have from light scattering. Now, the interesting part is that if I start to add a corrugation along this direction, we can start transforming these pancakes into an array of tubes. So for example, when the transverse confinement is deeper than the axial confinement, you can see that instead of pancakes, we have an array of tubes that we can control by like squeezing the tubes as making the lattice confiner deeper. And all the way here, we have just 3D points where you have atoms completely frozen. You see, unfortunately, the coherence time here is very small because of light scattering. So, but the important part is that we have been able to explore and compare with theory why is the reason of this change of contrast as a function of the lattice depth. And if you visualize each of the tubes, what we can see is that the tunneling along perpendicular to the tube is very small. So we can model the system as an array of different tubes. It's almost unit field, where at least at the center, where we are seeing that the motion is set by the super exchange interactions with a rate that is now here. I mean, you can see this is slightly different is because the tight transverse confinement from the laser beams actually introduces a little bit of curvature that we need to account in addition to gravity. But the important part is that they were able to actually see a pattern of the contrast as a function of time that is totally consistent with super exchange interaction. So the solid is the theory without 3 parameters. So this is along, this is along this arrow that this arrow that is moving here. So there are different lattice depths. And this is the dark time. And you can see that they were interrogated for 2 or 3 seconds, and they see the change in contrast. They see the characteristic oscillations at a frequency that is consistent with the parameters of the lattice, where U ranges from 1 to 2 kilohertz, 14 hertz of the tunneling, and the confinement along the axial confinement is 74 with a recoil, and we just change the transverse confinement. Then we collapse of the curves, and they agree with the expected behavior. That is very exciting. And also, well, you see the frequency exactly as we expect. Moreover, just to check that, well, what happens as you make the system more dilute, the advantage or disadvantage is that because they have a strong Gaussian confinement, even if when they reduce the number of atoms that is not unit filling, we start to have regions where still super exchange happen because the single particles cannot hop from one lattice side to the other. So I'm almost done. Therefore, as you decrease the atoms from, they transfer some of the atoms from ground to excited. They blow up away the atoms in the ground state, and then they transfer back to the excited. And they can see that as a function of the density, in fact, the dense sample is the one that have more contrast decay as we expect from super exchange, because they have more areas where super exchange is happening. So with that, I think we are in a very nice point where all the ideas that we have proposed based on the existence of spin orbit coupling and super exchange start to come into reality. So we are trying to see how we can use these contact interactions for actually generating spin squeezing. We are going to try to see, these are proof of principle, how we can generate icing interactions that in principle could lead the path for generation of cluster states. We have ideas of how to use these super exchange interactions to generate lattice states. And also because we have not only 2 nuclear spins, but up to 10, then we have ways to actually explore spin orbit coupling and analogs of quantum Hall physics, fractional Hall physics. And I'm running out of time. I wanted to explain a little bit what was the path of spin squeezing that we wanted to explore, but I mean, maybe I led these 2 questions and I just finish here. Because sorry, yeah, this was, I mean, at the end is how we are going to generate spin squeezing in the clock. That's our goal, and hopefully this will happen soon. But I cannot, I'm going to stop this plot by showing a picture of Bill, who has been always the inspiration of since I came here. And all the time that I see him, he really is excited about clocks and about the changes of the standard system of units, unification for the quantum SI. And I'm hopefully, we can do the dream that I'll have in the near term, that is really operate with entangled clocks. I mean, we are working really hard towards that. Well, this idea is not so in the near-term future, but maybe we can show that in the clocks we can have super coherence and therefore do some interesting ways that we can do entangled states. And this is the part that we are also really excited about. I mean, trying to explore the interplay between gravity and quantum mechanics. Not quantum gravity necessarily, but the interplay between gravity and classical gravity and quantum mechanics in the same system. And with that, thank you for your attention.
Well, Bill is also the theorist, so that's why.
Yeah, I know.
Right, okay, so yeah, questions?
So you started by saying that in the older generation clocks, the sort of collisions were starting to dominate the systematic error budget. Is the gravitational redshift actually now dominating the error budget, the systematic errors? Like, where is the clock and how much snow is there on the mountain?
Yes, well, that's true. I mean, no, because this is in principle something that they can control. I mean, yes. So, I mean, the dream is that, in fact, at some point, this is the most important systematic. So there are, what I can say. Of course, they measured the gravitational redshift, but this was measured for this is synchronous comparisons. So the actual clock, you don't want to do synchronous comparisons necessarily. Yes, you have to have really a universal standard. And so far, it's not at the accuracy, it's not at the -21. The accuracy is at 10 to the -19. And that's the latest report that Yoon had. But maybe in the future, I mean, when we are going to have been able, we were able to control all of this, I mean, the systematic is going to improve at that level. So still ways to go, but I mean, at least at the synchronous, when you compare the two parts in this clock, is not.
Right.
That gets to one of my questions. I may have missed it because I stepped in a few minutes late. How does he define zero in the plots that raise term zero? Does he do a density extrapolation, or does he have two plots?
He has two parts of the clock. He has it for the redshift.
Well, no, for even the density dependent measurements that cross zero.
This is yes. So he's looking. Yes, he does an extrapolation to very low, small atom number. It's an extrapolation. Yes. But also he can actually, now he's able to resolve very small regions of the cloud. So it's not in the last measurement, it's not a global comparison, but it's trying to compare different regions of the cloud. So local measurements in one part compared to the other, and he can compare. But yes, it's extrapolated to one atom.
Questions? No? Okay.
Okay, and so could you tell me a little bit more about how to use the gravity to induce the entanglement generation?
Yeah, I mean, this is a proposal that we have. It happens that if you have a Hamiltonian that is S.S, if you create a fully polarized ensemble, it's not going to do anything because it's SU2 symmetry. If you have a Hamiltonian that is S.S plus Hi sigma Ci, then this S.S opens a gap between the S equal to n-half and S equal to n-half minus 1. Yes. So basically, if this gap is larger than the inhomogeneity, you project the Hamiltonian into the inhomogeneity into the fully collective manifold. So the full projection of Hi sigma Ci, that is the gravitational redshift, the first projection is just the average of H SC, that is not important. But the second order projection is SC squared. So you can, introduces spin squeezing. So it's a slope. So At the moment, I think you need a 1 meter clock to see it in reasonable time scale. But I mean, there are ways that maybe we were able to enhance the production of squeezing. But yes, it does generate the squeezing, the interplay between collective interactions and single particle effects.
Okay, so there'll be tea with the graduate students, postdocs at the usual time. Let's thank Anna Maria again.